Dear students, welcome to the fourth session of our chapter 4 Chemical Bonding and the Molecular Structure. Today, we will discuss about the topic polarity of bonds. In reality, no bond or a compound is either completely covalent or ionic. Even in the case of a covalent bond between two hydrogen atoms, there is some ionic character. How we can explain this thing? As we know that both the hydrogen atoms are having one electron in them. What happens to that one? That hydrogen, they will share mutually the electrons between the two hydrogen atom and forms a covalent bond. If you consider the two hydrogen atoms, and then we can understand that one hydrogen will lose the electron and the other one will gain the electron. In that case, what happens? Is it a covalent or ionic bond? It is a ionic bond. Then how we can say that it is purely covalent bond between the two hydrogen atoms? So there are cases where we can't explain it properly. Now we know that there are two different types of covalent bonds. One is non-polar covalent bond and the other one is polar covalent bond. When covalent bond is formed between the two similar atoms like two hydrogen atoms, that is hydrogen molecule, oxygen molecule, chlorine molecule, nitrogen or fluorine molecule, the shared pair of electron is equally attracted by the two atoms. And as a result, what happens? The electron pair is situated exactly between the two identical nuclei. And the bond so formed is said to be non-polar covalent bond. Now, how we can explain the polar covalent bond? In the case of heteronuclear molecule like HF, hydrogen fluoride, both the atoms are of different element. That is, one is hydrogen and the other one is fluorine. The shared pair of electron between the two atoms gets displaced more towards the fluorine. Why? Because of the electronegativity. And in the case of hydrogen and fluorine, hydrogen is having more or greater electronegativity compared to hydrogen. That's why the electron cloud will move towards the fluorine. And the resultant covalent bond, we can name it as polar covalent bond. With a diagram, we can explain this type of covalent bonds. You can see here the first example is for the hydrogen molecule. And here equal sharing of electron is there. That's why we can see here the structure or the diagram where the two electrons are at the center of the two nuclei. Right? Equally distributed. So no electronegativity difference is there because both the atoms are same. But on the other hand, polar covalent bond, we have taken the example of HF. And H and F, who is having the electronegativity more? Fluorine. Here it is represented with a sign, that is delta minus, and this one is delta plus. This is said to be partial positive charge and it is having a partial negative charge. And here the negative charge is more in the case of fluorine. That's why when the combination of hydrogen fluoride is there, the electron will move towards the fluorine, which is having more electronegativity. That is unequal sharing of electrons we can see in the case of polar covalent bond. So this is how we can explain the two types of covalent bonds by the sharing of electrons. Next, we have to see the dipole moment. A dipole moment arises in any system in which there is a separation of charge. They can therefore arise in ionic bonds as well as in covalent bonds. The dipole moments occur due to the difference in electronegativity between the two chemically bonded atoms. And it is a measure of the polarity of a chemical bond between the two atoms in a molecule. And it is also a vector quantity since it has both magnitude as well as direction. It is usually designated by a Greek letter mu. And mathematically, how we can express this dipole moment is equal to q, that is charge, into distance of separation. Distance of separation is taken as r, or radius we are taking, and it is usually expressed in the unit of debye. Debye the symbol for debye is capital D. The conversion factor, that is, if we want to convert any unit from this to that, the 1D is equal to 3.33564 into 10 raised to minus 30 coulombs meter. So where C is the coulomb and M is the meter. In chemistry, the presence of dipole moment is represented by the crossed arrow, which is put on a Lewis structure of the molecule. The cross is on the positive end and the arrowhead is on a negative end. We can see here the example of hydrogen chloride and how we can represent the dipole moment of this molecule. We have to make first the Lewis structure of this hydrogen chloride. H with 1 electron and chlorine with 7 electron. And 1 electron they will share, making a covalent bond. That means hydrogen is having a partial positive charge and chlorine will getting a partial negative charge. When we are asked to put the dipole moment or the presence of dipole moment, we have to represent how we will put the arrow. Over this we have to put a crossed arrow. So where is the cross? It's on the positive part and the arrowhead will be on the negative end. This way we can explain the dipole moment in any of the molecules. And this sign or the arrow symbolizes the direction of the shift of electron density in the molecule. That means how is the electron density we can understand through this arrow, or where it is more we can understand through this arrowhead. Let's see the dipole moment in water molecule. As we know that water molecule is having a formula H2O, that means 2 hydrogen and 1 oxygen is there. If we make the covalent bond between them, we know that 1 electron is shared with this oxygen, making a duplet for each hydrogen. And oxygen was having 6 electrons and it will take 1 electron from both the hydrogens, making 8. And we know that hydrogen is less electronegative compared to the oxygen. So the dipole moment, when we want to represent, we have to point the arrow towards oxygen, both the cases, right? And this water molecule has a bend structure. The two OH bonds are oriented at an angle of 104.5 degree. The net dipole moment of 6.17 into 10 raised to minus 30 coulomb meter is the resultant of the dipole moments of two OH bonds. Both the OH bonds resultant dipole moment is 6.17 into 10 raised to minus 30 coulombs. The net dipole moment mu is equal to is given as 1.85 D. And if this D should be converted into coulomb meter, what we have to do? 1.85 into 3.33564 into 10 raised to minus 30 coulombs meter. When you do the calculation, we are getting the answer in coulomb meter as 6.17 into 10 raised to minus 30 coulomb meter. So this is what the dipole moment of water. Now let's see the dipole moment in beryllium fluoride. It has a linear structure and the angle between the bond is 180 degree. That is, linear means, of course, we know that it is having a bond angle of 180 degree. And here also we know that compared to beryllium, fluorine is more electronegative. So when we draw the crossed arrow, it should be pointing towards the fluorine. The dipole moment in the case of beryllium fluoride is 0. This is because the two equal bond dipoles point in opposite direction. You can see both are going in opposite direction and they cancel the effect of each other. That's why the net dipole moment becomes 0 in the case of beryllium fluoride. Now let's see the dipole moment in boron trifluoride. It has a symmetrical trigonal planar geometry. And here also the dipole moment is 0 even though the BF, that is boron and fluorine bonds, are oriented at an angle of 120 degree to one another. The three bond moments give a net sum of 0 as the resultant of any two is equal and opposite to the third. And we can see here the diagram how the representation is there for the dipole moment. Boron with an angle of, or BF bond is there with an angle of 120 degree, and the crossed arrow is towards what? The fluorine, because it is more electronegative than boron. So towards the fluorine the arrow is pointing. All the three cases. This is how we can represent the dipole moment in boron trifluorine, and the dipole moment becomes zero because the resultant of any two is equal and opposite to the third one. So it becomes zero. Now let's discuss this question. Which out of NH3 and NF3 has higher dipole moment and why? The molecular geometry is pyramidal for both the case. Both the molecules, they possess the pyramidal geometry. And in each molecule, we can see here nitrogen is at the center. And it has how many valence electron? 5. Out of 5, 3 is used for the bond formation of hydrogen in ammonia, and 3 is used in the case of NF3. So, the remaining one lone pair is there on the nitrogen atom in both the cases. The dipole moment of ammonia, that is 1.47, is higher than that of the dipole moment of NF3. 0.24 D is there. So which is having higher dipole moment? Ammonia. And why it is higher, we can see, or we can understand through this diagram. We can see here the NH3 molecule with the center atom nitrogen. 3 hydrogen atoms are there, and the lone pair is represented here. When the dipole moment we have to represent, the nitrogen will be more electronegative. So the arrow should be pointing towards the nitrogen. In all the cases, it will be pointing towards the nitrogen, and there is what? The electron pair on the nitrogen. So it's also showing upward direction. That means both are in the same direction, we can understand in the case of ammonia. Whereas in NF3, the nitrogen is there and the 3 fluorine atoms are there along with a lone pair of electron. The nitrogen is more or less electronegative. First we have to see. In this case, nitrogen is less electronegative compared to fluorine. So, the dipole moment will be pointing towards the fluorine atoms. So, all the cases it is pointing towards the fluorine. That means the resultant dipole moment will be going in opposite direction, because the lone pair's direction is upward, and this dipole moment towards the fluorine, it is going downward in opposite direction, we can see. This is because the NH3, in the case of NH3, the orbital dipole due to lone pair is in the same direction. We can see here both the directions are same. As a result, the dipole moment of NH3 bonds and NF3, the orbital dipole is in the direction opposite to the resultant dipole moment of 3 NF bonds. The orbital dipole, because of the lone pair, decreases the effect of the resultant NF bond moments, which results in the low dipole moment of NF3. So this is how we can understand that NH3 ammonia has higher dipole moment compared to NF3. Thank you. We'll continue in the next.